Consider the following problem that is known as the cutting stock problem in the literature. A woodworker can buy wooden boards of a certain length, say a length of 10 units. For a project, she needs smaller pieces that are to be cut out of the boards. She needs n different kinds of pieces, say n equal to 3. For the project she is going to build, she has a known demand for the different kinds of pieces. Suppose that she needs d1 equal to 7 pieces of length 3, d2 equal to 9 pieces of length 4, and d3 equal to 3 pieces of length 5. The question is, how should she cut the long boards into smaller pieces, such that a minimum number of wooden boards are needed? As always, you may try to model this problem by yourself and pause the video now. To begin with, let's investigate the problem a bit further. What alternatives for cutting a wooden board are feasible? One feasible cutting pattern would be the following. We could cut one piece of length 3 and one of length 5. Then we would have a waste of length 2. Now try to make a list of all feasible cutting patterns by yourself and pause the video now. Here is a list of cutting patterns. Note that feasible patterns that have a waist longer than the smallest piece are excluded from this list. You could add them, but if you think about it, considering such patterns wouldn't improve the objective function value. In total, we have a set of k equal to 6 cutting patterns that describe how we could cut a wooden board into a maximum number of smaller pieces. To describe such a pattern formally, we can use a parameter aij to denote the number of pieces of type I that are cut if we use the cutting pattern j. The second pattern in our list, for instance, can be described by Given these patterns, it's now very easy to formulate a model. All we need to decide upon is the number of times that we use a particular pattern. Let an integer decision variable yj be used to denote the number of times pattern j is used. This rather simple model describes our problem. The trick of this model formulation is to define solutions, or partial solutions to be more precise, as parameters. The problem then becomes a problem of choosing the partial solutions to be used and determining how often these partial solutions should be used. The downside is that the number of alternatives, the parameter k in our model, is quite large in some applications because there are many solutions possible. But there are special solution techniques to handle this when you want to solve such a model. This, however, is out of the scope of our video on modeling.